Okay, so let's look at example 51. This example involves conditional distributions. So consider the experiment of tossing two fair dice and recording the up faces. Let x1 and x2 be the minimum and maximum number showing, respectively. So we have looked at this situation. We've looked at this experiment before where we're tossing two fair dice and recording the up faces. We've looked at defining two new random variables on the sample space of this random experiment, where x1 is the minimum value, x2 is the maximum value. In a previous example, we found the joint PMF and the joint CDF of this bivariate distribution. And so now what we're going to do is, and we've also found the marginal distributions. Now what we're going to do is find some conditional distributions. And so specifically, for each value of x2 in the space of the random variable x2, we need to find the conditional PMF of x1 given x2, as well as the conditional CDF of x1 given x2. And then for each value of x1 in the space of the random variable x1, we're going to find the conditional PMF of x2 given x1, as well as the conditional CDF of the conditional distribution of x2 given x1. And then continuing on, once we have found the conditional PMFs, we're going to find for each value of x2 in the space of x2, we're to find the conditional mean of x1 given x2. We're also supposed to find the conditional variance of x1 given x2, as well as the skewness and kurtosis of the conditional distributions of x1 given x2. And then finally, doing the analogous thing for the conditional distributions of x2 given x1. For each value of x1 in the space of the random variable x1, find the conditional mean of x2 given x1, find the conditional variance of x2 given x1, and also find the skewness and the kurtosis of the conditional distribution of x2 given x1. And so the first approach that we're going to use is to, because these are discrete random variables, we're going to go back and look at the tabular representation of the joint PMF, as well as the tabular representations of the marginal PMFs as well. Okay, so let's look at the tabular representation of the joint PMF, and this will also have the marginal PMFs as well. Okay, so we saw this this tabular representation in a previous example, and inside the body of the table, this is where we have the values for the joint PMF associated with the combinations of x1, the minimum, which are listed down here in the bottom, the rows, the columns, and x2, which is the maximum of the two dice showing, and those values are given here in the rows. And for combinations that are of x1 and x2 that are not in the sample space, the cells contain 0. The sample space would correspond to those combinations of x1 and x2 where there are positive values in these cells. Now, in addition, in the margins of the table, we have the values that are taken on by the marginal PMF. And so the values up here in the column totals at the top, these are the values taken on by the marginal PMF of x1. And so, for example, the marginal PMF of x1 evaluated at 1 is equal to 11 over 36. The value taken on by the marginal PMF of x1 evaluated at 2 is 9 over 36, and so forth. Over here on the right-hand side, in this right-hand column, we have the values taken on by the marginal PMF of x2. And so the value taken on by the marginal PMF of x2 evaluated at 1 is 1 over 36. The value taken on by the marginal PMF of x2 given at x2 equal to 2 is 3 over 36, and so forth. Now, looking back in the notes, the first thing that we are asked to do is the first bullet point. For each value of x2 in the space of the random variable x2, find the conditional PMF of x1 given x2. Okay, and you'll remember that the way that we compute the conditional PMF is to divide the value of the joint PMF divided by the marginal PMF. And so in this case, if we're conditioning on x2, then we are going to be computing this conditional PMF, the conditional PMF of x1 given x2. So we're going to divide the joint PMF by the marginal PMF of x2. Okay, so that's what we're going to do to find the conditional PMF of x1 given x2. Now, we can see how we do this. Again, we've got the values of the joint PMF inside the body of the table. And in order to find the conditional PMF of x1 given x2, we're going to be conditioning on the value taken on by x2. x2 can take on the 6 values 1 through 6. And so we're going to find the conditional, for each of these values, x2 equal to 1 through 6, we're going to find the conditional PMF of x1 given that value of x1. Given that value of x2. And so, for example, when x2 is equal to 1, what we need to do is divide the values from the joint PMF of x1 and x2 by the value taken on by the marginal PMF of x2. Now, in this case, when x2, the max, is equal to 1, there's only one value that x can take on, and that is 1, because x1 has to be less than or equal to 2. And so to get the conditional PMF of x1 given x2, we're going to divide this joint probability by this marginal probability. So we divide 1 over 36 by 1 over 36, and we get 1. And because there are zeros here, the values of x1 being equal to from 2 to 6 are not even in the space of x1 for that particular situation. And so the conditional PMF of x1, given that x2 is equal to 1, is going to be 1 as long as x1 is equal to 1, and it's going to be 0 otherwise. And so let's take a look at how we would represent that. So here we're looking at the conditional PMF of x1 given x2, and in particular given that x2 is equal to 1. And so based on what we just saw using that tabular representation, the conditional PMF of x1 given that x2 is equal to 1 is going to be 1 as long as x1 is equal to 1 and it's 0 otherwise. Now, once we have the conditional PMF of x1 given x2, and in particular given that x2 is equal to 1, then we can find the conditional CDF of x1 given that x2 is equal to 1. Based on this PDF or PMF, the conditional CDF is equal to 0 if we evaluate it at any value of x1 that's less than 1, and it's 1 if we evaluate it at any value of x1 that is greater than or equal to 1. Next, we want to find the conditional PMF of x1 given that x2 is equal to 2. So we'll again go back to our table, and we see now that there are 2 positive values in this row inside the joint probability part of the table. And so when x2 is equal to 2, there are 2 possible values that x1 can take on, 1 and 2. To get the conditional PMF of x1 given that x2 is equal to 2, we're going to divide each of these joint probability values by 3 over 36. And so that would, if we divide 2 over 36 by 3 over 36, we get 2/3. And if we divide 1 over 36 by 3 over 36, we get 1/3. And so that gives us what we need to compute, or to determine, to write down, to express the conditional PMF of x1 given x2. So it's equal to 2/3 if x1 is equal to 1, and it's equal to 1/3 if x1 is equal to 2, and it's 0 otherwise. Once we have this conditional PMF of x1 given that x2 is equal to 2, we can very easily construct the conditional CDF of x1 given that x2 is equal to 2. That conditional CDF is going to be equal to 0 if we evaluate it at any value of x less than 1. It's going to be 2/3 if we evaluate it at any value of x1 greater than or equal to 1 but less than 2. And then it's going to be equal to 1 if we evaluate it at any value of x1 greater than or equal to 2. We continue on. We want to find the conditional PMF of x1 given that x2 is equal to 3. And so now we're focusing on this row. Okay, we see that there are three positive values taken on by the joint PMF. And so when x2 is equal to 3, there are three possible values that x1 can take on: 1, 2, and 3. To get the values that the conditional PMF is equal to, we divide each of these joint PMF values by the marginal PMF of x2 evaluated at 3, which is 5/36. And so 2/36 divided by 5/36 is 2/5. We get the same value for this cell. And then for this cell, dividing 1/36 by 5/36, we get 1/5. And so to find the conditional PMF, or to write down the conditional PMF of x1 given x2 is equal to 3, this is what we've got. That conditional PMF is equal to 2/5 if x1 is either 1 or 2, and it's 1/5 if x1 is equal to 3. It's 0 otherwise. Once we have the conditional PMF, we can again easily find the conditional CDF of x1 given that x2 is equal to 3, and it's given by this expression here. Continuing on, we want to find the conditional PMF of x1 given that x2 is equal to 4. Now we're working with this row, and I'm not, you can see exactly what we do. And so I'll continue on to the next slide here. The conditional PMF of x1 given that x2 is equal to 4 is going to be equal to 2/7 if x1 is equal to 1, 2, or 3. It's equal to 1/7 if x1 is equal to 4, and it's 0 otherwise. Then the conditional CDF of x1 given that x2 is equal to 4 is given by that representation there. The conditional PMF of x1 given that x2 is equal to 5, that conditional PMF is equal to 2/9 if x1 is either 1, 2, 3, or 4. It's equal to 1/9 if x1 is equal to 5, and it's equal to 0 otherwise. And then we, again, from that conditional PMF, very easily find the conditional CDF of x1 given that x2 is equal to 5. And then finally, for when x2 is equal to 6, the conditional PMF of x1 given x2, that PMF takes on the value 2/9. And this is, I see a typo here. I need to have 5 here and then a 6 down here. So make sure you write this down correctly. So it's 2/9 if x1 is equal to 1, 2, 3, 4, or 5, and it would be equal to 1/9 if x1 is equal to 6. And then we have the expression, and there's a typo here as well, that needs to be 6. So just make sure that you type that in correctly. I'll fix that when I get into the notes. Okay, so now we want to find the conditional distributions of x2 given each of the values in x1 that x1 takes on in its sample space. And so going back to the joint probability table, now we're going to be conditioning on x1, and so we're going to be conditioning on these values taken on by the marginal of x1. And so to find the conditional PMF of x2, given that x1 is equal to 1, we notice that when x1 is equal to 1, x2 can take on the values 1 through 6, and the values taken on by the conditional PMF will be these joint probability values divided by this marginal probability value. So we divide each of these by 11/36. And so when we do that, we see that the conditional PMF of x2 given that x1 is equal to 1 is going to be equal to 1/11 if x2 is equal to 1, and it's going to be equal to 2/11 if x2 is either 2, 3, 4, 5, or 6. It will be 0 otherwise. conditioning on x1 being equal to 2. If x1 is equal to 2, then the only values that x2 can take on would be 2 through 6. To get the values taken on by the conditional PMF of x2 given x1 equal to 9 over 36, we divide these joint probabilities by this marginal probability. And so we get the conditional PMF of x2 given that x1 is equal to 2 being equal to 1/9 if x2 is equal to 2, and it's 2/9 if x2 ranges from 3 up to 6. It's 0 otherwise. Once we have this conditional PMF, we can find its conditional CDF as given here. And let me just back up. So here is again the conditional PMF of x2 given that x1 is equal to 1. And here's the corresponding conditional CDF. Moving on, if x1 is equal to 3, then we're going to divide these joint probabilities by the marginal probability. And that's going to give us a conditional PMF of x2 given that x1 is equal to 3. It takes on the value 1/7 if x2 is equal to 3, and it takes on the value 2/7 if x2 is equal to either 4, 5, or 6. It's 0 otherwise. And then from this, we can construct the conditional CDF of x2, given that x1 is equal to 3. And we continue on conditioning on these subsequent values of x1. And so when we do that, we get the conditional PMF of x2, given that x1 is equal to 4, taking on the value 1/5 if x2 is equal to 4, and 2/5 if x2 is equal to 5 or 6. 0 otherwise. And then we have the conditional CDF down here. When x1 is equal to 5, the only possible values that x2 can take on are 5 and 6. And so the conditional PMF of x2 given that x1 is equal to 5 will be 1/3 if x2 is equal to 5 and 2/3 if x2 is equal to 6. And then from that we calculate the conditional CDF. And then finally, when x1 is equal to 6, there's only one possible value that x2 can take on. It gets all the probability, and so the conditional PMF of x2 given x1 equal to 6 is 1 if x2 is equal to 6, and it's 0 otherwise. Okay, and then from that we can easily construct the conditional CDF. So that's how we can construct the conditional PMFs using the tabular representation. We can also construct or derive the conditional PMFs analytically, if we so choose. And so let's see how to do that. So let's first look at the conditional distribution of x1 given the value given x2. So remember that the conditional PMF of x1 given x2 is defined in the following way. As long as little x2 is in the sample space of x2, then as long as it's such that this marginal PMF of x2 is positive, then the conditional PMF of x1 given x2 is equal to the ratio of the the joint PMF of x1 and x2 divided by the marginal PMF of x2. Now you'll recall that the conditional PMF of x1 and x2 is given by the following representation. It's equal to 2 over 36 if x1 is strictly less than x2, and that x1 and x2 are both integers 1 through 6. It's equal to 1 over 36 if x1 and x2 again are both integers from 1 to 6, and x1 is equal to x2, and it's 0 for any other possible combination of the values of x1 and x2. Similarly, and from the joint PMF, which we derived this earlier, the marginal PMF of x2 is equal to 2 times x2 minus 1 over 36, as long as, and this should be an x2 here, that's a typo, if x2 is an integer from 1 to 6, and it's 0 otherwise. So we need to divide this joint PMF by the marginal PMF, and in order to get this conditional PMF of x1 given x2. And when we do that, this is what we get. the conditional PMF of x1 given that x2 is equal to little x2 can be expressed concisely in the following way. It's 2 over 2 times x sub 2 minus 1, as long as x1 and x2 are both in the integers from 1 to 6, and x1 is strictly less than x2, and it's equal to 1 over 2 times x2 minus 2, or 2 times x2 minus 1, as long as x1 and x2 are both integers from 1 to 6, and x1 is equal to x2. And then this conditional PMF is 0 otherwise. Now, once we have this conditional PMF of x1 given x2, we can derive the conditional CDF of x1 given x2, and it's given by this expression here, this piecewise defined function. And recall that the CDF has to be defined for every at every real value, at every real number, and so we utilize here the you'll remember this as the greatest integer function here in this representation. Okay, so that is how we can come up, derive these values analytically. Let's see how we derive the formula for this conditional CDF of x1 given x2. So let's fix the value of x2 to be one of the integers from 1 to 6, because those are the only values of x2 that we can condition on. Then for a fixed value of x2 in that set, the sample space of x1 consists of the integers from 1 up to and including x2. Now, it therefore follows that the conditional CDF of x1 given x2 is going to be 0 for all values of x1 less than 1. It's going to be 1 for all values of x1 that are greater than or equal to x2. And then for values of x1 that are greater than or equal to 1 and strictly less than x2. And remember, when we consider this, we're letting x1 be any real number in that range. It's not restricted to being integers. And we take care of that by using the greatest integer function. So in this situation, the conditional CDF of x1 given x2 is going to be the sum, k going from 1 up to the greatest integer that is less than or equal to x1, of the conditional PMF of x1 given x2 evaluated at k, all right, which is the index of summation, given this particular value of x2. Now, based on the expression for the PMF, this is, because x1 is strictly less than x2, the conditional PMF evaluates to 2 over 2 times x2 minus 1. Now, we can, since this does not depend on k, we can pull it out front. And anyway, we go through a simplification, and this turns out to be 2 times the greatest integer that is less than or equal to the argument, x1, over 2 times x2 minus 1. So that is, so from if we combine these three results on the last two slides, we get the fully specified expression for the conditional CDF of x1 given x2 given by this piecewise defined function. It's 0 if x1 is less than 1. It's 1 if x1 is greater than or equal to x2. And then it's 2 times the greatest integer that is less than or equal to x1 over 2 times x2 minus 1, as long as x1 is any real number that is greater than or equal to 1 and strictly less than x2. And this applies for these values of x2, the values of x2 in the sample space of that random variable. Now, likewise, we can construct or derive the conditional distribution of x2 given x1 analytically. And so again, remember that in order to come up with the conditional PMF of x2 given x1, all right, which is denoted this way, we divide the joint PMF by the marginal PMF of x1. So and also recall from our previous examples and previous work that, again, the joint PMF of x1 and x2 is given by this expression, this piecewise defined function. And also, the marginal PMF of x1 is given by this expression, 13 minus 2 times x1 over 36. All right, now combining these two results, utilizing definition for this conditional PMF of x1 given x2, we get the expression, the piecewise defined function for the conditional PMF of x2 given x1. It's equal to 1 over 13 minus 2 times x1, as long as x1 and x2 are both integers between 1 and 6, and x2 is equal to x1. And it is equal to 2 over 13 minus 2 times x1, as long as x1 and x2 are both integers from 1 to 6, and x2 is strictly greater than x1. And then for any other value of x2, the conditional PMF of x1 given x2 is equal to 0. Now, once we have this, we can derive the conditional CDF of x2 given x1, and it's given by the following expression. It is 0 if, as long as x1 and x2 are both integers from 1 to 6, and x2 is less than x1. It's equal to 1 if x1 and x2 are both integers from 1 to 6, and x2 is greater than or equal to 6. And it's equal to 2 times the greatest integer the greatest integer that is less than or equal to x2 minus x1, 2 times the quantity of that difference there, plus 1 all over 13 minus 2x1. As long as x1 and x2 are both integers from 1 to 6, and x2 is greater than or equal to 1 and less than or equal to 6. Now here is how we actually derive the formula for the conditional CDF of x2 given x1. We're going to first fix x1 in the set of integers 1 through 6. When we fix a value of x1, then the sample space of x2 becomes the set of integers from whatever x1 is up through and including 6. It therefore follows that the conditional CDF of x2 given x1 is equal to 0 if x2 is less than x1, and it's equal to 1 if x2 is greater than 6. Now, let's consider the situation where x2 is greater than or equal to 1 and less than or equal to 6. Now, there are 2 cases to consider. The first case is when x2 is equal to x1. And so in this case, the conditional CDF of x2 given x1 evaluated at x2 is the same as the conditional CDF of x2 given x1 evaluated at x1 because x1 and x2 are equal. Now, this turns out to be the probability that x2 is less than or equal to x1, the conditional probability. I should have included the conditioning here, but I haven't done that to save room. And we can decompose this as the probability that x2 is strictly less than x1 union with the event x2 is equal to x1. Now, these 2 events are mutually exclusive, and they're connected with union, or, and so we can decompose the probability of their union with the sum of their individual probabilities, and that is via axiom, by axiom 3. Now, the probability that x2 is less than x1 is 0, and so we're left with the probability that x2 is equal to x1. This is given by the value of the conditional PMF of x2 given x1, which is 1 over 13 minus 2 times x1. So that is the value of the conditional PMF of x2 given x1 when x2 is equal to x1. When x2 is greater than x1 and less than or equal to 6, then the conditional CDF of x2 given x1 evaluated at x2 is equal to the sum, k going from x1 up to the greatest integer less than or equal to x2, of the conditional PMF of x2 given x1 evaluated at this index of summation k. Now we can decompose this sum into 2 pieces. The part where k is equal to x1, the first value that k takes on, and then the rest where k is strictly greater than x1. Now, the conditional PMF of x2 given x1, when x2 is equal to x1, that's 1 over 13 minus 2 times x1. And then we have, when k is strictly greater than x1, then this this conditional PMF evaluates to 2 over 13 minus 2 over x1. And so then we have this, we can simplify this. Notice that I'm pulling 1 over 13 minus 2x1 out of this sum and simplifying. And so we get 2 times the quantity, which is the difference between the greatest integer less than or equal to x2 minus x1, 2 times that difference plus 1 over 13 minus 2 times x1. Now, when x2 is equal to x1, then this simplifies to 1 over 13 minus 2 times x1, which is the same formula for the conditional PMF of x2 given x1 obtained under case 1. Hence, the formula obtained under case 2 simplifies to that obtained under case 2 when the conditions of case 1 are met. And so the results of the two cases can therefore be combined so that the conditional CDF of x2 given x1 can be written more succinctly as 2 times the quantity, which is this difference between the greatest integer less than or equal to x2 minus x1, 2 times that difference plus 1 over 13 minus 2 times x1. And that applies for all values of x2 that are greater than or equal to x1 and less than or equal to 6. And so putting these results together, the fully specified expression for the conditional CDF of x, the CDF, because that's what we're deriving here. The conditional CDF of x2 given x1 is given by the following expression. It's 0 if x2 is strictly less than x1. It's 2 times that difference between the greatest integer less than or equal to x2 and x1, plus 1 all over 13 minus 2x1 for values of x2 that are greater than or equal to x1 and less than or equal to 6, and then it's 1 as long as x2 is greater than or equal to 6. Now we're going to obtain the raw moments of the conditional distribution of x1 given x2 in several ways, analytically and also computationally. And from these raw moments, we'll calculate the central moments and then eventually the skewness and kurtosis coefficients. Now, in the process of deriving the raw moments, we're only going to go through the first two raw and central moments. To get the third and fourth central moments, we're going to rely on computation. So let's see how we do this. So first recall that the conditional PMF of x1 given x2 is given by this succinct formula. And so for values of x1 and x2 in the set of integers 1 through 6, where specifically x1 is strictly less than x2, then the conditional PMF of x1 given x2 evaluates to 2 over 2 times x2 minus 1. And for values of x1 and x1 equal to x2, it evaluates to 1 over 2 times x2 minus 1. And so we can use that expression to analytically derive the first raw moment. And so again, that is denoted the expected value of x1 given that x2 is equal to some particular value in its sample space. And so by definition, that's going to be the sum, x1 going from 1 up to x2, because x2 is the largest that x1 can be, of the products, x1 times the conditional PMF of x1 given x2 evaluated at that value of x1 given the value of x2. Now we're going to decompose the sum into the first x minus 2 terms, x2 minus 1 terms, and then the final term where x1 is equal to x2. And we do that because over those two ranges of values of x1, the conditional PMF evaluates differently. Specifically, for values of x1 that are strictly less than x2, the conditional PMF evaluates to 2 over 2 times x2 minus 1. And when x1 is equal to x2, it evaluates to 1 over 2 times x2 minus 1. Now, once we have that decomposition, we can go through some fairly straightforward computations, some algebra, and some evaluating. For example, this sum here is fairly straightforward. And we end up getting, for the expression for the first raw, the conditional first raw moment, we get x2 squared over 2 times x2 minus 1. Now remember, this is the conditional expected value of x1 given the value of x2. All right, and so this is it's a function of x2, the value that we are conditioning on. And so once we have that expression, we can evaluate the conditional expectation of x1 given x2 for each value of x2 in its sample space, which consists of the integers from 1 up to 6. And so for each value of x2 in that set, the first raw moment of the conditional distribution of x1 given x2 is given by these values. So the first raw moment of the conditional distribution of x1 given that x2 is equal to 1 is 1. The conditional expectation of x1 given that x2 is equal to 2 is equal to 4/3 or 1.3333. The conditional expectation of x1 given that x2 is equal to 3 is 1.8 or 9/5, and so on. So we see here that the expected value, the conditional expectation of x1 given a particular value of x2 depends on x2. It's a function of x2, and in particular, it's given by this expression here, which we're evaluating on this slide. All right, now we can also calculate the second raw moment, and so we use the same kind of approach. The conditional expectation of x1 squared, given that x2 is equal to a particular value in its space, is given by the sum x1 going from 1 up to x2 again, this time of x1 squared times the conditional PMF. We then utilize a similar decomposition of the sum, and then going through some computations, some algebra, things like that, we end up getting the expression x2 times the quantity 2 times x2 squared plus 1, all over 3 times 3 times the quantity 2x2 minus 1. And so then we can use that formula, all right, to calculate the second raw moments of the conditional distribution of x1 given x2, and we get the values here. The expected value of x1 squared, given that x2 is equal to 1, is equal to 1. The expected value of x1 squared, given that x2 is equal to 2, is 18 over 9, or 2, and so forth. So we have, and we have both here a fractional representation, which is exact, and then a decimal approximation, right, out to 4 decimal places when necessary. And so once we have the first 2 raw moments of the conditional distribution of x1 given x2, we can calculate the conditional variance of x1, given that x2 is equal to 2. And so and I'm going to utilize the computational formula. All right, so the variance of the conditional distribution of x1 given x2 is equal to the expected value of x1 squared, given that x2 is equal to 2, minus the square of the expected value of x1 given that x2 is equal to 2. So utilizing those formulas, we get this formula here, which we can then use to calculate the variance. And so these are the values for the variance of the conditional distribution of x1 given x2. And you can see that the conditional variance does in fact depend on the value of x2 at which we're conditioning. And so it's a function of x2. And so here are a couple plots. I've got this plot is the expected value of x1 given x2, and it's plotted as a function of x2. And so we see that it's an increasing function of x2. And here is a plot of the conditional variance of x1 given x2. Now, in addition to calculating these quantities analytically, oh, and by the way, we have not yet calculated the third and fourth raw moments, nor the central moments of the conditional distribution of x1 given x2, and therefore we've not calculated the skewness and the kurtosis. The calculations do get a little bit more involved as we get to those higher order moments, and so I'm going to, instead of using an analytical approach, I'm going to use a computational approach, and I'm going to show you how we can calculate all these quantities using a computational approach without having to go through and do the algebra. And so what we're going to do is utilize spreadsheets and or a calculator such as the TI-84, and that's what I've done. I've done it both ways and created some output to show you, so you can choose how you want to do it. I strongly recommend that you make a template spreadsheet. This is a recommendation that I've made to you in the past, and if you've not done it yet, I highly recommend that you do it, because you are going to need something like that for at least one of the upcoming labs. And it's really going to make the work much quicker for you if you have such a spreadsheet. And so let me first start off by showing you these, how to obtain these results. And so again, hold on, let me go backwards here. So again, obtaining the raw moments of the conditional distribution of x1 given x2, and by using the spreadsheet and the TI-84, we're going to obtain not only the first two raw moments, we're going to obtain the first four, and we'll obtain all these quantities, plus additionally we'll get the skewness and the kurtosis of the conditional distribution of x1 given x2 using these spreadsheets and also using the calculator. So here is the spreadsheet for the conditional distribution of x1 given x2, in particular given that x2 is equal to 1. And since we've already derived the formulas for the conditional PMF of x1 given x2, all we're having to do here is input the appropriate conditional PMF into the spreadsheet. Now this one's fairly straightforward and fairly boring, right? There's only one value in the sample space of x1, given that x2 is equal to 1. And notice that the variance is 0, which it has to be because it's a degenerate distribution. There's only one value in its sample space. Because the variance is 0, then the skewness and the kurtosis are not defined. Now let's look at the situation where we're conditioning on x2 being equal to 2. Okay, and so here we have the sample space along with the values of the PMF, and then the mean, variance, skewness, and kurtosis for this conditional distribution get computed automatically by the spreadsheet. And then we have the situation where we're conditioning on x2 equal to 3, and again the calculations are done very easily, and we get the mean, variance, skewness, and kurtosis for the conditional PMF. The situation where x2 is equal to 4, all right, we get these values. And I have a summary page that I'll show you in just a moment that has all these values. So we're not going to spend time looking at these spreadsheets very long, but I just wanted to show you, once you have that spreadsheet template, it's going to be very easy for you to calculate these things. So you don't feel like you have to mathematically or analytically derive formulas for these moments, as I showed you a few moments ago. You can certainly do that if you want, but you don't feel like you have to. For the purposes of assignment, the lab assignments, and so forth, it is quite sufficient to use a spreadsheet or a calculator to calculate these quantities computationally. Okay, now let me also show you how to obtain these values using the TI-84 calculator. Okay, so this is for the situation where we're conditioning on x2 being equal to 1. And this is that situation where it's a degenerate distribution. There's only one value in its sample space, and therefore that one value has a probability of 1. The format of these pages here are going to be the same for all the values of x2 that we're conditioning on, from 1 up to 6. So the first cell is going to have the conditional PMF. Then I'll have the conditional mean, as is indicated above. And then I'll have the conditional variance. And then when the conditional skewness and kurtosis are defined, I'll have those screenshots down in these two cells. But since in this situation the variance is 0, the conditional skewness and the conditional kurtosis are not defined. But these cells do show you how you can calculate the conditional mean, conditional variance, and then the conditional skewness and kurtosis using the functionality of the calculator. And so for when we're conditioning on x2 being equal to 2, all right, then all of these moments and characteristics are defined because, in this case, the variance is positive. And so you can see here how we can calculate not only the mean and the variance, but the skewness coefficient and the kurtosis coefficient. All right, here's the output for the results when we're conditioning on x2 being equal to 3. And you can compare the values obtained here with those that we showed previously, that we looked at, and also in my summary page that I'll put up in just a moment. And here's a situation where we're conditioning on x2 being equal to 4. All right. For x2 being equal to 5. And then finally for x2 being equal to 6. And then here is an overall summary. This shows the conditional mean, the conditional variance, the conditional third central moment, from that and the variance, the skewness coefficient, the conditional fourth central moment, and then from that and the conditional variance, when defined, the conditional kurtosis coefficient for each value of x2 that we are conditioning on from 1 up to 6. And so this is just a summary page that shows you these quantities for each of these values of x2. So you can take a moment, maybe pause the video and make note of these so that you can compare, if you want to compare them across the various ways that we've computed these, analytically, computationally, feel free to do that. Okay, let's move on. Okay, and now we've already done this. So let me. Now we're going to look at obtaining the raw moments of the conditional distribution of x2 given x1. And again, we're going to utilize this approach where we try to obtain them analytically or mathematically, and then we'll follow that up with a computational approach. And again, don't feel like you've got to derive things mathematically for the purpose of lab assignments. It's perfectly acceptable for you to use computational approaches using spreadsheets, calculators, programming in some other language. That's perfectly fine. So, okay, the conditional PMF of x2 given x1, for values of x1 and x2 in the integers from 1 to 6, specifically where x2 is equal to x1, all right, it evaluates to 1 over 13 minus 2 times x1. When x2 is greater than x1, then it evaluates to 2 over 13 minus 2 times x1. And then for any other values of x1 and x2, the conditional PMF of x2 given x1 evaluates to 0. And so, again, we're going to first obtain the first raw moment, the expected value of x2, given that x1 is equal to some value in its sample space. And what I'm going to do here is decompose this sum into the first term in that sum, and then the last terms. And the reason we're doing this, again, is because when x1 is equal to when x2 is equal to x1, then the PMF evaluates to 1 over 13 minus 2 times x1. And for values of x2 that are strictly greater than x1, the conditional PMF evaluates 2 over 13 minus 2x1. And so once we have that decomposition, then we can just proceed as we in similar ways as we've done in the past, and we come up with a nice expression, a nice formula, all right, for the conditional expectation of x2 given x1, and that formula is 42 minus the square of x1 over 13 minus 2 times x1. And so we can use that to get the specific values for the expected value of x2 given that x1 is equal to a particular value by plugging in x1. And so we get these values here, which I'm just representing in their exact values as fractions. So the expected value of x2 given that x1 is equal to 1 is 41 over 11. The conditional expectation of x2 given that x1 is equal to 2 is 38 over 9, and so forth. We obtain the second raw moment for the conditional distribution of x2 given x1 in a similar way. And when we do that, we get the formula 546 minus 2 times the cube of x1 minus x1 over 39 minus 6x1. And so we get these values for the second raw moment of the conditional distribution of x2 given x1. In other words, the expected value, the conditional expectation of x2 squared given x1. And so we have these values. And then once we have the first two raw moments of the conditional distribution of x2 given x1, then we can come up with a nice formula for the conditional variance of x2 given x1. All right, so I'm not going to read that off, but you can see it there. And then once we evaluate that, at each value of x1 ranging from 1 to 6, we get the conditional variance of x2. Oh, I've got a typo here. I see that now. You see, I should have the variance of x2 given x1 is equal to 1, not the variance of x2 squared. So I'll need to correct that in my notes, but as you copy this down, make sure that you don't have that squared there. Okay, so I fixed that in the notes, and by the way, I noticed that, let me go back to the previous computations. I also had that same problem here, and you may have noticed that, but I've corrected that in these notes. So make sure that if you're writing this down, you don't have the variance of x1 squared, which would be incorrect. You have the conditional variance of x1 given that x2 is equal to each of these values. So I've corrected that in the notes, and okay, so now we're at this page, and so again, we're just using this fairly straightforward formula that we've derived to compute the conditional variance of x2 given that x1 is equal to each of these different values, each of the 6 values in the sample space of x1. And so again, I've created, I've used these formulas for the conditional mean and conditional variance of x2 given x1 and created plots. And we see that these quantities functionally depend on the value of x1 that we're conditioning on. And so we can see what these functions look like. Okay, so I also, in addition to this analytical approach or the mathematical approach, I want to, again, just go over very quickly the computational approach to calculating these various characteristics of the conditional distribution of x2 given x1. And so again, we can do it via spreadsheets. And so this would be, here I have the conditional PMF of x2 given that x1 is equal to 1. And then from that conditional PMF, it's calculating all of these raw moments. And from the raw moments, using the expansion formulas for the central moments, it is calculating the conditional mean, conditional variance, conditional skewness, and conditional kurtosis. And when x1 is equal to 2, these are the results. And I'll just continue on here. Here are the results when x1 is equal to 3, and then when x1 is equal to 4, and so on. And so, again, feel free. In fact, I really want you to create one of these template spreadsheets for calculating these moments and characteristics, because it's going to be very, very helpful for you. A big time saver when you go to do some of the subsequent lab assignments, and also perhaps some of the examples that we'll see in the future. Okay, then we have, let's see here, we can also do this on the TI-84. So again, here are the commands that you would use on the TI-84 to compute the conditional mean, variance, skewness, and kurtosis for the conditional distribution of x2 given that x1 is equal to 1, or any value of x1 in its sample space, once you have input the appropriate conditional PMF into the list as shown here. And so here we have the situation for x1 equal to 2, x1 equal to 3, x1 equal to 4, and then x1 equal to 5, and finally x1 equal to 6. Okay, and then we have a summary page, again, containing the conditional mean, variance, skewness, and kurtosis, along with the conditional third and fourth central moments of the conditional distribution of x2 given x1 for each value of x1 in its sample space. So you might want to write these values down, and as you work through this example, which I highly think you should do, highly recommend that you should do, and compare your results to what we've obtained here. And so this, let me go ahead and close these out. Okay, so again, here are the plots. Okay, but that's the end of this example. And as you can see, it was quite an involved example. So I think I'll end this particular lecture video. And in the next video, we're going to pick up looking at doing these same kinds of computations for continuous random variables.